Oh, that one actually worked first time. Alright, so in this video we're going to be talking about classifying numbers, and so this entire chapter really focuses on our different number sets, primarily rational and irrational numbers. But it helps if we understand all of our number sets, and so we've mentioned integers, we hear about whole numbers a lot, so we're going to actually go through and define those. So our smallest number set is the natural numbers. These are numbers we count by. So numbers we count by. That's the simplest definition I can give you. So that would be, when we count, what this comes down to is when we count, we don't start at 0, we start at 1. And so we're going through 1, 2, 3, 4, and we continue. So, but that includes like 1 million. Technically, I don't want to count to 1 million, but I can count to 1 million. It is just our numbers, our whole numbers without 0. So then when we get to whole numbers, we just add 0. So this is our natural numbers, those natural numbers we count by, plus 0. So, for example, let's put these in pretty brackets so we know it's a number set. 0, 1, 1, 2, 3, 4, and it goes on. Alright, so natural numbers are numbers we naturally count by. We don't start with 0. Whole numbers, we just add that 0 in to our natural number set. Integers are the whole numbers and their opposites. So when we show this set, that would be like -3, -2, -1, 0. And I should have started with dots to begin with. 1, 2, 3, and end with our ellipses. And so, whereas before with natural and whole numbers, our continuation was at the end, with integers it's on, but we're going both directions. So that's our whole numbers and their opposites. So the 1 with the -1, the 2 and the -2. Whereas our rational numbers, we just recently defined, right? These are numbers that can be written as fractions, terminating decimals, and repeating. Oh, helps if the and actually starts writing. Repeating decimals. Oops. So that includes our integers, whole numbers, and natural numbers, because I can take each of those numbers and make them into a fraction. Irrational, it means not rational. So, cannot be written as a fraction terminating decimal or repeating decimal. And then real numbers are all the above sets. Oops, let me erase stuff. So if it's a natural number, a whole number, an integer, a rational, or irrational number, then they are real. These are numbers that exist. I can put them on a timeline. Or a number line. Alright, so to kind of help us understand how these are all related, we're going to create a Venn diagram. And if you would like to make a physical one of these, I have the materials, and you can make them. So we start with our biggest box, or circle, however you want to do it. All right, and this is what we're going to call our real numbers. And inside our real numbers is another fairly big box that we're going to call our rational numbers. And outside of that rational number box, we're going to have another box. That's going to be our irrational numbers. And inside our rational box, we're going to draw one. And this one's going to be our integers. And then inside our integers exist our whole numbers. And then inside whole numbers exists the natural numbers. So it helps if we have some examples, right? So our natural numbers would be like the number 7 or 4 over 2, because what is 4 divided by 2? Well, it's 2. The square root of 25, because the square root of 25 is 5, which is a number that we count by. Our whole numbers, the only thing we add to the whole numbers is the number 0. Other than that, everything that is a natural number is a whole number, which is why, because when you think of a Venn diagram, what overlaps is the same. So our natural numbers is inside the whole numbers, which means that every natural number is also a whole number. And if you notice, both of them are inside the integers, which means that if it's a natural number, it's a whole number, it is also an integer. And so then your new numbers for integers are things like -3, negative 15 over 5, because -15 divided by 5 is a -3. A negative square root of 16, because the square root of 16 is 4, so then that would equal -4. And then both natural, whole, and integers all fit within rational numbers. And the only thing that adds to the rational numbers are numbers like 2/3 or -3/5. Our decimals like 0.25 or 0.3 repeating, because repeating decimals are also rational numbers. So the only numbers I've written in the boxes are numbers that don't belong in one of the other boxes. Because if it's a rational number, and here's where it can get confusing. If it's a natural number, it is within the whole numbers, within the integers, within the rational. But not all rational numbers are integers, right? This 2/3 is not an integer. That 2/3 is not a whole number. The 2/3 is not a natural number that I count by. I don't sit there and go, all right, 1/3, 2/3, 3/3, 4/3. It's not how I naturally count. But my natural numbers fit within all of them. If it's an integer, it's rational, but it's not necessarily a whole number or a natural number. I have to look at, is it the positive or is it the negative? If it's a negative whole number, then it's not really a whole number, it's just an integer and rational. So those are things we have to think about. Irrational numbers. These are things like the square root of 10, or 1.010110111, and that pattern continuing. Pi is a popular irrational number. E is also, you can look into that number, natural number E. Negative the square root of 123. Irrational numbers because it doesn't fit in one of the others. But all of these are real numbers. Alright, so let's go through and classify each. 15. Can I count to 15 naturally? Yes, so that means it's a natural number. And if it's natural, then coming back here, natural is whole, is an integer, is a rational. So, natural, we know that it's a whole number. We know that it is an integer. We know that it is rational because I can make this a 15 over 1. And it is obviously real. Negative 1.232. Just because it's negative does not make it an integer, because an integer is the positive and negative whole numbers. But it doesn't continue, it terminates, which makes it a rational number. And it exists, so it's real. Square root of 45. If we go back to our notes from the last section, 45 is not a perfect square, which makes this irrational. And because it's irrational, it's none of the other subgroups. It is just irrational and real. Moving on to our next. 121 over 35. Well, that's a fraction. So going here, fractions start in the rational numbers. So we're just rational and real. Square root of 16. And actually, I think this was one of them in here, right? Square root of 16 is 4. We put the negative in front of it. That makes this a negative 4. So a negative 4 is an integer. I guess we were just calling that I. Is an integer. And if it's an integer, it is also rational and real. So if we go back here, if it's an integer, it is also rational and real. Alright, those are our headings. 21 over 3. It's already written as a fraction, right? So we know that it's rational, but what else do I know? If I take 21 and divide by 3, I get 7. So where does 7 land in all of these? Well, it's a natural number. I can count by it. And if it's natural, then it's whole, then it's an integer, then it's rational and real. So when it's a positive whole number, we're hitting all of them. Natural, whole, rational, or integer, rational, real. Now, it didn't just give it to us as a whole number, it gave it to us looking like a fraction. But I have to think, does my denominator divide into my numerator evenly? And if it does, then I have to go ahead and do that so I can think of that. But that's how we can classify a number. And then that is all for classifying numbers.